Hi, and welcome. Flink at Workday, scaling of ingested data pipelines to S3. In this presentation, Leir and I will introduce you and walk you through our effort to scale our data pipelines toward S3. We will start looking at the background and challenges in implementing a streaming platform in Workday. We will overview our ingestion jobs, and then we will dig a little bit more technical with the improvements that we have done to the S3 sync to keep up with the performance requirements that we had, and how we implemented a logic to observe the ingestion. If we will have a bit of time, we will also introduce two appendix on how we tested our jobs and how we evolved the job logic without breaking SafePoint compatibility. Let's start with Workday. Workday is a leading provider of enterprise cloud application. So we deliver service for financial human capital management, planning, and analytics. Because of our requirements and our customers that are more than half of Fortune 500, we have very strict security needs. More specifically, we can see how Flink at Workday has been told. Workday is based on the success of Workday was initiated with a monolith service. So we had just one big code base that was then distributed on multiple machines to handle all the services. Via the expansion and the growing of the company, we had more and more external services and microservices in general that needed to communicate with this monolith and with other services. So we had the need of transport, massage, and verify data that is passing through multiple services. More specifically, machine learning, that is the team where we work in, had the need of computing models and transporting data to compute models. And this couldn't be done for each of the tenants in a separate way. We had to have a unique service that handled all this amount of data. Flink gave us all these possibilities. But to implement Flink in our company, we had two opposite requirements that drove the architecture design of this streaming platform. The first is multi-tenancy. As we say, we have multiple tenants where a tenant is a representation of a customer, but we need to process data in a single place, or we need to be able to process multiple tenant data in a single place. This goes against the requirement that is set in our company, where each piece of data is always encrypted at serialization with the key provided by the tenant that generated this piece of data. So whenever two tenants generate two pieces of messages, each piece of message throughout all the platform needs to be encrypted always with the correct key from each of these tenant that generate the data. If you want to dig a little bit more on this requirement, I suggest you to look at the Flink Forward presentation from 2019 in Berlin, where we introduced how we added encryption at the serialization layer in Avro. Now I pass the presentation to Leire that will introduce you to the current challenges.
Hey guys, I'm going to start my section by giving you, actually not there yet, a little snapshot of where we were at the time of these improvements and where we wanted to get to, given the requirements that Enrico already has mentioned. So in 2019, what do we have? We had a S3 ingestion job that was okay, but it was a bit lagging. There was a few bottlenecks. On the one side, we had this CPU usage for encryption decryption that was very high, which is the tenant encryption decryption. And there is here a link for that presentation that Enrico mentioned that we did last year. And on the other hand, there is also that the data distribution we deal with is very complex. On the one side, we have streaming data, which means loads of different types of messages from different tenants going at the same time, ingesting data on more than 4,000 buckets. And on the other side, we have batch extractions that have up to 150 million messages per batch, but all of them are of the same type and from the same tenant. So with these challenges, we set ourselves a few goals for 2019, 2020, which first, the two, not small per se, but not as priority, which were automating and simplifying the operational load. We have all our jobs in the same OpenStack framework. And it was quite difficult for us to scale for getting more jobs on board. And also we were lacking a little bit on test capacities because we were going quite fast when developing these jobs. But most importantly were the last two ones, which is handle this constant traffic from so many tenants and so many different schemas or message types. And also being able to monitor such traffic, because being able to get things through but not seeing if the results are correct or if the data is not corrupted, that was also a big deal. With this said, in 2019, we had these numbers, which is we had 6 jobs. They were deployed across 6 data centers on OpenStack. We were ingesting hundreds of millions of messages, which is not bad, and 100 Avro schemas. From this landscape, we went to 2020 to have 7 jobs plus 2 that will be deployed in production soon. We still have the 6 data centers on OpenStack, plus 4 coming up soon on Kubernetes, on AWS. We have more than 11 billion messages ingested per week. And the Avro schema number also has doubled. So you can see the changes are quite significant. But for doing this, it wasn't a very easy journey. So what did we do to get to this point, to fix these bottlenecks that we had in the ingestion job? I'm going to give you a bit of an overview on our ingestion job. It's quite standard as it is. We have, I'm going to select this little pointer. So we have the monolith that Enrico talked about earlier, which is where all the data lives for Workday. That is going to generate messages being sent to Kafka, where they get stored. And then our Flink job here is going to read from Kafka. The Flink job itself has more or less the usual pieces. So it has metrics, some filters, validation, and then the sync that will post the messages then to S3. And then we have S3 itself. So nothing super major, apart from the challenges that we mentioned before, that was like business requirements. So before we started these improvements, what did we have? We had a bucket and sync, which is the standard for Flink 1.4 and commits files one by one to S3. And we just went ahead with this because it was the default. In here, we observed that there were 2 factors that when in combination were slowing us down. One of them was the actual S3 integration, and the other one was the high number of tenants. And what I mean by this is that if we removed any of the 2, then we didn't have problems. So no S3 integration, loads of tenants, okay. S3 integration and 1 tenant, okay. But together, not so okay. So this for us was unsustainable, as we can't really limit our business case to 1 tenant or no S3. And then we started trying to address these issues. The first attempt that we thought of was windowing. So we thought that perhaps by aggregating messages of the same type in a window and then posting them all at the same time to S3 will make our jobs faster or give them higher throughput. But unfortunately, this didn't work. And the problem in here was that even with this windowing, we still had way too many buckets running in parallel. All this array of buckets were having these writers open, and they, after 60 seconds, they get rotated. So as they were being addressed, the ones that were in wait were still being rotated, giving even more lag to the whole process. And lastly, some of the checkpoints were taking over a minute because of the flushing and renaming of each file in S3 taking around 5 seconds. So all in all, not great. So we went a little bit further and went for the second attempt, which was try to implement the streaming sync. This streaming sync was suggested to us by the Flink community as an alternative to try to get these issues addressed. But yet, unfortunately, this didn't work. And Why was that? Mostly because the version of the Cloudera distribution of ATFS that we have in Workday is too old and does not support multi-part upload. That was a major issue, but there was also a couple of other things. Even with data stream in sync, we still will be doing file closing synchronously, which is not ideal. And also there were some challenges in trying to implement this logic that if you are curious, you can see there is a thread in the Flink community with this that details these issues. So there we were, second attempt. And finally, we did find the real root cause of the slowness. So there's this piece of code in the bucket in sync that is going to check if a file exists in S3, and if it doesn't, it creates it. And this is called every single time a message is saved in the bucket, which the profiling showed it took an average of 3 seconds. So this realized, okay, we have a problem with this bit, and we actually don't need this piece of code. Then we went on to the implementation of the successful attempt, which was to implement the two-phase sync interface that Flink provides. And what we did with this is removing the slow check, the one that I showed just earlier. We decided to keep all these messages, all this data in state, as opposed to having to send them to S3 and then rotate the file. And this also allows for exactly one in S3. On top of that two-phase sync, we also extended the implementation to have a threshold because we keep everything in state, which is faster. But also if there was too many messages, that would pose a problem for state and then for checkpoints or whatnot. So we implemented this for a threshold, and even more, we went and changed that rename feature. So if we have more messages than this threshold, we will put them first in S3 as an in-progress file and then rotate them at commit. And this rename, we switched it to be a pure AWS client to improve performance, as opposed to using the default one in HDFS in Flink. And lastly, we also massively parallelized the write operations at commit to avoid having them done synchronously and then having all these waits as well. So here's a little snapshot of the code. Obviously, it's much longer than this, but this is just to understand the two-phase commit sync function that we extend on our sync. There is the begin transaction, which is when like a writer is created, or well, a transaction and hence a writer is created where the messages start coming through. We have then the pre-commit that is also written and the commit. Nothing super breaking ground here. And here's a little animation for you to see a little bit how it works. So first, when a message of a type, and I'm going to talk about keying later, but we have keys that are a combination of the tenant, schema, and batch ID. So when a message of these features comes in, then the writer is going to get instantiated for that key, and it has a message cache where these messages are going to be stored as they come in. Once the first checkpoint after this arrives, then the writer is going to get closed and put in the pre-commit queue. If at this stage there is more messages with this key that arrive, then a new writer will be instantiated before the pre-commit on the start transaction, and it will store those messages as a separate step. And whenever yet another checkpoint arrives, then that means that those messages in that pre-commit queue will be sent to S3. And lastly, I'm going to talk a little bit about keying and partitioning. So we decided to key our messages because that way we had a little bit more control with the partitioning. So by default, each key is going to be processed by one slot. And this key, as I said, is a mixture of the features of that message. So tenant, schema, batch ID. The partitioning is going to allow us to decide which type of messages are going to be dealt with by more slots than one or not. So for example, we have streaming data. This data is of a very varied array of tenants, schemas, and hence, even if one slot deals with one particular key, the variety is such that all slots will be busy at any given time when there is throughput. But for batch, because all those messages are pretty much the same key, schema, and tenant, then they will be processed by only one slot, which is not ideal because then all the other slots will be idle. So then by doing this partitioning, we are assigning for batch. We want it to be partitioned by age. We want everything to be dealt with by every slot. But for streaming, keep it just on one. And that way we also avoid having to serialize and deserialize all these messages between slots. And now I'm going to pass it over to Enrico to tell you how we make sure that these results were actually correct.
Yeah, thank you. Thank you, Dara. So we are going to go ahead and look a little bit at what we have done in terms of logic to understand specifically the second case discussed by Larry, so for batch jobs. So just to repeat it, batch jobs are jobs that are kicked off by our monolith, distributed on multiple nodes, and generates a huge quantity of data. They are 150 million messages. Remembering that each message is a business transaction, so it's not very lightweight. It could be multiple hundreds of kilobytes. And we want to have visibility on when the batch is completed. We want to have visibility because we have other logic that have to kick off out of the data that we ingest. For example, here you can see a really high-level representation of our job. You have a source, some metric emitter, some filters to remove or manipulate a little bit the data in case it's not valid. Then a final validation that will reach out to an external system to validate if this job for this tenant can extract data. And then we send the data to S3. Now, when all this data is to S3, we want other services to be notified that they can use it to generate, for example, new models. How we do that? Well, the requirements are mainly those. So we need to be able to report when the batch are finished, given that the batch may take up to 12 hours to be ingested. Then we want to have a way to signal flexibly to other services via Kafka, via file written on a specific path, or via other logic that we want to introduce in the future. And this signal may contain information like the message received, message rejected, the tenant, the schema that we used, and other kind of information. But the third and probably the most important requirements for our implementation was that we want to signal this only when we are sure that the data is available on S3 to be ingested. And now we are gonna show you a little bit how we have done the various parts and why the third problem was a problem. So let's start on how we can group and collect all this information to signal it. First of all, we introduce a new secondary flow. So a parallel flow to the main one where we collect the stats, this metadata of all the messages that we ingest to calculate the status of these ingestions. We have done this by introducing a generic function that extract the metadata to a secondary flow. You can see here important, let me go back. Here important is that we extract a key out of the metadata of the message, and then we extract the stats itself. And we're gonna send it to this side output with a tag, so we are able to understand if this kind of information is at source or at sink. Now we can collect this information. You can see that here in the code, we grab the information from this two-side output. We put it into a stream. We union them. We key them by the key that we assign to each key. And then we send it to a function that is keyed. It's a keyed function that allows us to aggregate all the information per key. The key, as mentioned by Larry before, is the tenant, the job ID, and the type of data. Now, at first, the function doesn't do anything special. You can see here that the two main functions, there is much more code, but the two main functions are a process element and timer. Where in the process element, we do, first of all, we try to flush the stats, all this information that we have, and we will come back to this function in a minute. Then we will initialize the state of the keyed state of this operator. We will update the timer, so to have a timeout in case the batch completes and we don't have any more messages, but the flash of the data didn't kick. Then we process the batch message. So effectively, we analyze this single message and we aggregate and we calculate the new stats, and we report them here in the keyed state. In the timer, I mentioned it here in the code just to remind ourselves that we always need to consider the case, as I mentioned before, that we don't receive any more message for a batch, but we need to do some post-processing. Now, we have seen the code to allow us to aggregate and compose stats, but how we do the reporting, especially with this requirement that we have seen early in the slide before, this third requirement that we want to signal it only when everything is done. So the challenge here is that the access to the checkpointing, so the way that effectively the Flink job will write to S3, because we use a two-phase sync, is provided by the checkpointing function. But the functionalities or the capability to write to an output, so to the next operator, so for example, to signal it, is provided only by the process and timer function. So you can see that this code is separated in two ways and called in very different contexts. So the process and timer functions are called in a keyed context, and instead the checkpoint that is not called is called by operator. So we have two different pieces of code that need to dialogue. How we have done it, we have tried to bring these two together, so to have the checkpoint and registering the state, and then the processing function reporting the state outside to the next operator. Let's see a little bit more. Here I'm gonna explain a little bit what happened. So here you can see the 4 reds are 4 messages for the same batch. We have said that here, whenever you receive a message, at the next checkpoint will be committed or pre-committed. So more in detail, these 2 messages will be pre-committed right before the checkpoint 2 and will be committed in an asynchronous function after checkpoint 2. So effectively, we can be sure that the data is stored in S3 only when checkpoint 3 arrives. And this is the moment that we want to report, for example, that is completed, or in the metrics that this message is effectively stored in S3. How we do that? We first collect whatever is in progress during this transaction to some local variable. Then at each checkpoint, using the checkpoint function, we copy this information to a state. You can see that we have 3 of them here. And then finally, at the first message that comes after the checkpoint is finished, we send this data out. In this specific case, during the commit state, we send to the next operator, or after a stat is added to the close state, we clean up the metrics to not have too many. Let me go a little bit through the code. It's a simplified code and misses some parts, but it allows us to discuss a little bit more about this implementation. Let's start from the bottom. So in the snapshot state is a function that is called right before a checkpoint is finished. So the Flink will call this snapshot state, and we will take the already committed states and we put it in the committed state. We take the local per partition and we put it in pre-committed. And then we can clear the local. So if we go back to the function, we are taking this local, we copy to the pre-commit, and we are taking the pre-commit and we copy to the commit. The close state is not reported here, just to keep a bit more compact the code. The second part that we can analyze is the notify checkpoint complete. So this function is called when everything about the checkpoint is successful. So Flink managed to do the checkpoint, so we can mark this checkpoint as complete, and so set our flag job status to be flashed as true. We are telling to the operator that effectively there are new data that can be flashed to the metrics or to the next operator. And here you can see the function that we have seen before, the first step of the process function of our operator, that every time a new message is arriving or a timeout is happening, we verify, is there new data to be flashed? If yes, we go to take all this information and we go to flush it to a generic output that could be the next operator or something from the context like metrics. Clearly here at the first, after this step, we set the flag again to false. So we execute it every time right after the checkpoint each time. In this way, we are effectively reporting when the data is in S3, and all the other services that are waiting for this data can pick up the work and go ahead. So just to recap, we have seen with LayerM how we had to improve the S3 sync to keep up with the performances needed by implementing the two-phase sync interface. Then we have seen how we observe all this ingestion, adding a secondary flow. And now that I have a little bit of time, I will work through the appendix. Specifically, I want to introduce, or I want to share a bit of our experience in testing our job. Initially, we didn't have much test, but we have found very, very important these three steps for our testing. So the first one mentioned here is to have a performance evaluator sub-project. So we have a sub-project in our main job Java project that can be compiled having different parameters. For example, we recompile our job with a jar that can be personalized and set different source and different sync. In this way, we have still a fed jar that can be deployed on any distributed system with parameters like a fake source or a fake sync, and really verify that everything into the job is working correctly without having to deal with the integration to external system. Another key to evaluate specifically the performance of the job, of the internals of the job, of the new operator that we wrote, it was to implement a message fire hose. We started from the Verberica example that you can find here at the Flink. A message fire hose is a fake source. So it's a source operator that generates as much data as much the rest of the job can ingest. So we'll generate all the data that is needed by the job to be really saturated. And you can, in that way, really verify the throughput of the operator and verify if you have any bottleneck or anything that is not working correctly. Finally, we also implement a local Kafka for integration test. So we have our integration test that stand up using this library from Salesforce, a local Kafka in the heap. And this allows us to test very particular distribution of the data, so we can use and play with partitioning, with different tenants, with different skew of data, and verify that everything is working correctly. As a second appendix, I wanted to mention this trick that we have found on how to evolve the logic of the sync. Writing out your own sync has the complexity that the transaction is a very key part of you can see in the code of the two-phase sync. The transaction is a very key part of your sync logic. And specifically, the serialization and the serialization logic and the way the data is defined can break always the safe point compatibility. How you handle changes that breaks the safe point compatibility, you can use it. You can do it via this piece of code. This example shows how to do it. So you can, in your main data flow definition, you can always instantiate the new and the old sync. You can see the before and before3. Then the data right before to arrive to the sync can be splitted and sending all the data to a v4 tag. And now you can see that we instantiate the old sync using the v3 tag that is never used here. So effectively, the sync will be instantiated by Flink, but it will not receive data. This allows us to stand up from a safe point. So if we have any data that is in fly, so in a transaction that needs to be committed after the pre-commit before the checkpoint, this will be done naturally because the operator, the sync comes online, but all the next data will go to the next sync that is instantiated here. Finally, the next step will be to the simple commit where you remove the v3 and your logic will be clean and running on the new sync. That's it. Thank you. Thank you for your time, and we hope that was interesting. Bye-bye.